All right, now you have your notes out. So you took notes yesterday over the significance of a chemical formula. Now, I would like for someone to tell me something about the video. First of all, where'd we start at? What was going on? Okay, we were dealing with nomenclature. Okay, we were dealing with nomenclature and our start of nomenclature. And the first thing we dealt with was a chemical formula. The significance of a chemical formula. And tell me, what's a chemical formula? What is significant about a chemical formula? Zoe? Sure you do. You watch the video. Tell me something about it. And then you better find your notes and look at it. Okay? Yeah. They indicate the number of atoms of each kind of element in a compound. So, if I would put something up here, something that I like to use, we're talking about this right now, because we're dealing with cellular respiration and photosynthesis. We're talking about this in biology. So, I have glucose up there. So you can tell me, you can look at the chemical formula of glucose and tell me how many carbons there are, right? How many? There are 6 carbons. How many hydrogens? 12. How many oxygens? 6. All right? So we know that we have 6 carbons, 12 hydrogens, 6 oxygens. Now, when it sometimes gets confusing is when we use the parentheses. Okay? So let's say that I have calcium phosphate, okay? Calcium phosphate, right there is the chemical formula for calcium phosphate. So I look and I say, all right, I have 3 calcium, right? I have 3 calcium. How many phosphate do I have? 2, because I know if there is no number behind an element, what does that mean? If there's no number behind, what does it mean? It means there's only one of them. So I can see there's 1 phosphorus, but since I have parentheses 2, I multiply that out. There are 2 phosphorus. How many oxygens? 8. So basically, really what I'm looking at by those parentheses is that I have 2 of those. 2 of those PO4s. So I would have 2 phosphorus, and I would have 8 oxygen. Now, certain things about these parentheses where we run into, okay? Where we run into. I see this all the time. People say, all right, I have 2 phosphorus, and I have 6 oxygens. Now, the people that do that have done what? Okay? They've taken the 4 right here, they've taken this 4 right here, and they've taken the 2 and they've added them together to get 6. Not correct. Okay? Not correct. It's multiplying those together. Something I also see, folks, is I see people who don't use their parentheses, and they go PO4, and I have 2 of them. Now, what that looks like to me is that I have 42 oxygens. Okay? 42 oxygens. Is that the case? Do I have 42 oxygens? No. So is it important? Is it important to put those parentheses in there? Yes, absolutely. Here's another thing that I see. Here's Here is the correct formula for calcium sulfate right there. Calcium sulfate is CaSO4. What I see people doing is this. They don't put anything past the parentheses, but they just have CaSO4. Now, early on when people do that, I just go, I scribble that out to signify, hey, you've got CaSO4, that is correct. You do not need those parentheses. Okay, you do not need those parentheses. But I can guarantee you, folks, when you take the test at the end of this chapter, if you have parentheses on that, bam, I'm going to mark it wrong. Okay? When do you need parentheses? When you have more than one. Do you have more than one here? No. So you do not need parentheses. Parentheses are only when there are multiple ones of that polyatomic ion. Okay? We only use parentheses with polyatomic ions, and you will learn about those today when you watch the video notes. You'll learn about polyatomic ions. All right? So after the parentheses, we started talking about ions. We started talking about ions. The example I used in the notes was fluorine. Today, what we're going to talk about is chlorine. Okay? I have chlorine right here, and we learned bonding. And we know, based on bonding that we did last chapter, that chlorine has has 7 valence electrons, right? Our bonding notes, our dot structure said, okay, chlorine has 7 valence electrons. So knowing now, and this is why we do bonding before we do naming, okay? Because it makes a lot more sense. We can apply what we learned on bonding to understand these ions. What is chlorine going to want to do? Add or lose electrons? It's going to add how many, Andy? Add 1 electron, right? Chlorine wants to add 1 electron. Now, right now as I look at chlorine, it has 17 protons, it has 17 electrons. Okay, so 17 pluses, 17 minuses. If I add 1 electron, now all of a sudden I have 18, ooh, that was funky, 18 electrons, right? So I have 1 more minus than I do plus, so my chlorine is now a -1. Now, chlorine is the name of the element. When I make it into an ion, I do what? I do what? Go ahead. Huh? I don't call it a chlorine. I have to do something. Okay, Josh? I keep the base. And then I put an IDE ending. Okay, so I keep that base of chlorine, and then I put IDE. So that is the chloride ion. The chloride ion. You know, we could do that with all of them. Let's say we got oxygen. What are we calling it? What are we going to call that? The oxide ion. What about nitrogen? It would be nitride. Sulfur would be sulfide. So all we have to do is add the IDE ending. Carbide. Okay? Carbide would be carbon, but we very rarely see that because carbon likes to covalently bond more than it likes to ionically bond. Also, folks, now what we're talking about with this whole bonding thing, when we discuss it, where is Where is chlorine going to get that 1 electron from? Okay. Well, how about sodium? When I have sodium, it has 1 valence electron, right? So wouldn't it make sense that sodium gives that 1 electron to chlorine? Because sodium wants to dump an electron, right? Makes sense. We talked about that in bonding. Well, when that happens, my sodium, sodium was 11 protons, 11 electrons. Now, all of a sudden, sodium has 10 electrons because it gave it 1 away, so it's going to have a 1 plus charge, right? Well, when I'm naming and writing formulas, my charges have to equal 0. If I'm using sodium, a +1 charge, and the chloride ion, a -1 charge, does that equal 0? +1 -1? Yeah. So when I am writing the chemical formula, it is going to be sodium chloride, NaCl. Now, let me show you when it's a little bit different, okay? When it's a little bit different is if I've got calcium, all right? Calcium has 2 electrons that it wants to get rid of, correct? So what happens, okay, what happens is that we are going to have a second chlorine. Because now the 1 electron will go there, the second electron will come right here. So now I have calcium who lost 2 electrons. When it lost the 2 electrons, it became a 2 plus. Now, can you see why I need to have 2 chlorines? So, when I write the chemical formula for calcium chloride, it is CaCl2, because I need 2 chlorines to get that net charge to be 0. I showed you on the video the crossover method. And I also told you that I don't use the crossover method. I don't use the crossover method because probably a slim part of the time, I'm going to say over 90% of the time, the crossover method is good. Okay? The crossover method is good. And if we look at that Ca, 2 plus, and that Cl, 1 minus, what I mean by the crossover method is if I cross the 2 over here and I cross the 1 over here, I get CaCl2. Isn't that what we just said calcium chloride was? Right? The example I gave you is Al, 3 plus, O, 2 minus. If I do the crossover, it gives me Al2, O3. Now, I don't use the crossover method. I use what I call the least common multiple. Okay, what's the least common multiple here of 2 and 3? Think a little bit about your math. Least common multiple is 6, right? Least common multiple is 6. So if I want to get aluminum to 6, I'm going to need 2 of them. If I want to get oxygen to 6, I'm going to need 3 of them, right? That's how I do it. Because finding the least common multiple doesn't lie to you. It's always correct. Yet another way that people see this better is, I look here, and I've had people do this, and at times when we were teaching this to younger kids, let's say younger, not lower level, younger kids, they see it better by saying, okay, I don't have equal charges. I have more pluses than I have minuses, right? So I have to get more minuses. Well, now I've got more minuses than I do pluses, correct? So I just keep adding these until I get my charges equal. Now are my charges equal? Yes. So I needed 2 aluminums and I needed 3 oxygens to get those charges equal. Okay. It doesn't matter to me what way you do it. Eventually, you'll be able to just look at it and say, okay, here's how I'm doing it. This is what it is. Now, the reason. Okay, let me show you why the crossover method doesn't work all the time. Here is something that we call lead, and we have lead 4. Okay? Lead 4 is lead with the 4+ charge. Oxygen. Oxygen's a 2-, right? If I do crisscross, I get Pb4. If I do crisscross, I get Pb2O4, right? Now, what do I get if I do the least common multiple? What's my least common multiple of these two? 4, right? So if I take lead to 4, I have what? 1 of them. If I take oxygen to 4, I have 2 of them. That is the correct answer. That is not. Okay? Just because it's the same proportions doesn't mean it's right. Okay? You could simplify it, yes. But that doesn't always work either, because let me show you why. Let me show you why you can't simplify it all the time. Okay? You could simplify that one, but look at this one. There is a substance, okay? There is a substance that is H1+. Oxygen at times, okay, is this, 2-. Okay? So I have, once I do this, H2O2. You ever heard of that? You ever heard of H2O2? Yeah, you have. It's hydrogen peroxide. Everybody's heard of hydrogen peroxide. You put it on your wound and it bubbles, right? Okay? Now, if you reduce that, you're wrong. You're wrong if you reduce hydrogen peroxide. So there's exceptions to all these. Okay? But if I take the least common multiple, it's not going to lie to me. It's not going to lie to me. Now, take out your ion sheets. Okay? Take out your ion sheets. I love the ion sheet. Let me see if I can find it here. You might know that I won't be able to find it. Well, that's because I'm not even in nomenclature right now. If I can find the ion sheet that I want, polyatomics, a list of common ion sheets. Here we go. This guy right here, you got this yesterday. Okay, you got this yesterday, and of course it's not going to let me do anything here. Okay, let's see if this will work. No. Okay, great. You got this yesterday, and I can't even move it. But on the back of that, there is a little periodic table. Oh yeah, now it moved. Okay, on the back of that, there's a little periodic table, right? That shows the different ions. Okay, now, it's not going to let me do it again. Thanks, technology, you're killing me here. Okay, but you have the little periodic table on the back side of that. I really, really like that because it helps you associate the charges with certain families. Look at your alkali metals, group 1. All of the alkali metals have a +1 charge, don't they? The second group there, the alkaline earth. All of the alkaline earths have a 2+ charge, right? Now if we look at, here we go. Here's what I'm talking about. Now if we look over here at the halogens, all of the halogens have a -1. If you look at the oxygen family, okay, if you look at the oxygen family, they're going to have -2s. So that table helps you associate some of the ions. Okay, I really, really like that table. Now, let's go through and let's work a couple writing formulas. Okay, we're going to start off with something that's sodium sulfide. Sodium sulfide. Now, how I'm going to do these is I'm just going to find the ions. Sodium has a symbol of Na, and what is sodium as an ion, and what is its charge? The sodium ion has what charge? Okay, the sodium ion has what charge? +1. Okay, look at that periodic table I just showed you. Right here, sodium, right? Right there, sodium is a +1. What was sulfide? Right here, sulfur, right? Sulfide is -2. So, if I am writing the chemical formula for sodium sulfide, I'm going to need to have 2 sodiums to make that net charge equal 0. Na2S. Now let's look. Okay, let's look at another one. Let's look at calcium phosphide. What's my charge for calcium going to be? It's going to be Ca +2, right? What am I going to get for phosphide? P, what? P3-. So, if I am writing the formula for this, it is going to be Ca3P2. All right? Now, ladies and gentlemen, believe me when I say that we are starting this off very slow, okay? You might look at that and say, man, this stuff's easy, okay? And eventually, trust me, it will be easy, okay? It will be easy because we're going to do so much of this the rest of the year that you're going to find yourself not even needing ion sheets. Okay? You're going to be naming these things bam, 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 because we do it enough. You're going to know that calcium's a 2+, phosphorus is a phosphide's a 3-. You're going to know some of the polyatomics will be committed to memory. Okay? But we're starting off nice and easy, binary ionic, binary meaning 2, so there's only 2 elements. We're going to throw in some polyatomics tonight, okay? So what you need to do